Thank you very much. Thanks for inviting me. Let's start. So let's start with definition of similarity search problem. In similarity search problem, you have an input. It's an algorithmic problem. And an input is a huge data set of objects. And say in this example, we have pictures. And then we have some time for preprocess them. So we need to build some data structure to keep our objects. And once we get a query is another object. And what we have similarity function or distance function that for any two objects provide distance or similarity, how similar they are. And our task is quickly to find an object in the data set which is the most similar to the query object. So can you solve this? I hope so. So that's your governor. And OK, so we find the most similar object in the data set. That's the problem. And the problem is to find a data structure that is small, ideally linear, in such a way that the search is fast, ideally something like logarithmic, not like comparing the new picture with every picture in the data set. So the outline for today's talk has 4 parts. First, I quickly overview what are applications of similarity search within web technologies. Then I quickly show you what is known in theory. And then I would argue that the model we study in theory is not exactly what we need for practical application in web. And then we put some new definitions and new open problems, mostly theoretical. And then I show you a couple of new algorithms. That's the plan for today. Please take the first place. Yes. OK, so applications. So that's the list. So usual application, say advertisement, is the following thing. You have a lot of ads in your database. And every advertisement is characterized by keywords, by a set of people who already clicked on that, by the website, its ranking. And there are plenty of characteristics. And there is a user with Google cookie. And so you know a lot of things about the user, like what was his previous search queries, what is he visiting, what is he writing in Gmail, I don't know. You know a lot about user. Some of information you probably do not like to use. You say we keep privacy. But some other things you consider to be useful for make more personalized advertisement. It's called behavioral targeting, when you target your advertisement to user that is likely, by his previous behavior, is likely to be interested. So you have a data set of all advertisements. There is a user with his profile. There is a similarity function or relevance function that say how similar the user profile is for every ad. And the question is, in what data structure should we keep our advertisements in order to very quickly identify the most relevant ads to a given user? So user is a query. Ads are objects in the data set. Another example is various kind of best match search. So usual web search is end search. You have query words, and you search for usually for pages that contain all of them. But if you put 100 of them, or you put some, say, example or some restrictions, if you are searching for car or apartment or boyfriend, girlfriend, I don't know, you set a lot of restrictions, constraints. And most probably, there is not a single object that satisfies all of them. So you're searching for objects that satisfy most of them. And that's called best match search. So the number of satisfied constraints is a similarity function between query and object. So there are plenty of different problems. And you probably should address them differently. But on very high abstract level, they all are like similarity search. So that's a typical example of how a similarity is how you can define similarity. So this is a picture about recommendation papers to scientists. So there is a scientist, and we would like to recommend him new papers to read. Please take places. There are a lot of free seats. First idea is to use keyword matching. Like this scientist is interested in similarity search. This paper contains these words. So let's recommend it. It's called content-based recommendations. Another idea is like use social structure. And using social structure means that you look at friends of this person And if one of his friends likes something, like his co-author already cited this paper, then it's likely this paper to be recommended to initial user. This thing is more tricky. Assume there is a paper I'm very big fan of. Maybe I'm just an author of this. And then we are trying to identify the similar objects to what I already like. So in particular, here there is a paper that is often co-cited together with my paper. So once somebody cites my paper, he already also cited another paper. Then there is a good idea to recommend the second paper for me to have a look. So the general idea that there are a lot of chains in these networks that can connect the query object and one of the objects in the data set. And the larger number of these chains, the shorter they are. And if we have weights, the heavier they are, the more likely this object to be similar or relevant to our query, in particular here to user. That was very brief description of application. So what's known in theory? So in theory, we have this abstract problem. And in abstract problem, we have some domain. Domain is the set of all possible objects. We have n objects, which is data set or database. We have a query object. And our task is to find the object in the data set that has the smallest distance, no, the highest similarity to query object. And there are, and there are plenty of particular models. So model means the data model, what is the object, and the similarity model, the answer to the question, what's the function of distance. So the typical example is like Euclidean space with Euclidean distance, or Euclidean space with scalar product similarity. So that's a typical models. Or for strings, if you care not about the set of words, but about their sequences, then you can use something like edit distance or Levenstein distance, the same name. Like what is the minimal number of operations you need to transform one string to another string. That's the measure of similarity. OK, so what is known in theory about that? There are several algorithms. There are a few of them are here. So, and you see that that's once you have an application and you see on that, look at that, and you're a little bit lost. So you don't know what to use. And for example, the geometric near-neighbor access tree was the first or the second paper by Sergey Brin. So he also participated in this competition in nearest neighbor algorithms. So I think that if you are working with some practical problem, instead of looking on all these papers that use a lot of specific choices, a lot of heuristics, and some elements from which they build their own algorithm, it's better to be aware of key ideas instead of all these detailed algorithms. Look at the ideas and reuse ideas, not the algorithms itself, in practice. So that's my personal choice of 4 great ideas. So I will briefly describe you, very briefly, what's they about. And if you are more interested, then you are welcome to my tutorial I have on my website, tutorial with full descriptions of all these methods. So the branch and bound is idea to keep all objects in a tree. And on every internal node, you have something like, say, bounding ball that cover all objects within this subtree. So if you have a root and you have, say, 2 children, then you have a ball that cover all points that are in the left branch. You have a ball that cover all points. OK, they may intersect, the balls. Cover points in the right branch. And when you have a query, and you probably have a search radius, so this is query, and you are searching for similar objects within this range, if this small ball doesn't intersect, say, left branch, then you skip the whole branch and go only to the right branch. If it intersects both, you need to go to both. So in general, there is no guarantees that you will not visit every object during this tree navigation. Probably you will visit everything. But sometimes if you have clever heuristic for partitioning, it can decrease amount of computation. The second idea is to use walks. And walks is the following idea. You start from some object in the data set and trying to move to another object which is more similar to query. And then you look around, and if you find an object which is even more similar, you move there. And so you do several steps until you arrive to such an object from which you cannot do any immediate step to improve your situation. And then sometimes you can conclude that that's the nearest neighbor. The third idea is to go to another space. So if you have plenty of objects in some very wired space, maybe 1 million dimensional space, and it's really hard to work there or do some like branch and bound there. So you probably first to map all this object to some much better space, maybe even discrete space or whatever. So hashing is a particular idea of mapping. And then you try to identify neighbors in this new space. And if the mapping does not affect too much the notion of being similar, then you probably find the problem easier in the new space. The last idea, which appears, I think, like 5 years ago in the context of similarity search and pretty new, is the idea to have the several like maps of your data set on every scale. So you start from one ball that covering all points, and this is your world map. And then you are trying to cover all points by balls twice less radius. So it's like country level. And so you see a picture that data set is covered by all these countries. And then if you zoom in, that there is a third level of balls of 1/4 radius that again cover a whole thing. And you can think that these are states or counties and so on. And so you have for every scale, you have the covering of balls that cover all the data set. And then your search is like jumping down. So you identify the most interesting region on every scale. So you identify the right country, then you look for right state, then you look for right county, and then you look for the most similar city. So that's the idea. So the data structure is like the several layers of these balls. OK, so now we can move to thinking whether the problem was stated correctly or not. So I showed you before this picture of chains that produce different contribution to overall similarity. So we can try to model that with graph theory instead of Euclidean space and Euclidean distance. Something like that. We have several types of nodes. We have probably weighted edges. We have restrictions on degrees because every scientist here wrote at most 100 or 200 papers, not like millions of them. But if you have citations, so every paper cites, say, 20 or 30 papers, but every paper can be cited by thousands. So there is different restrictions on out degrees and in degrees. And then we have this similarity chart that overview all contributions. And then we have some summing up function, maybe some coefficients. So this is much more mathematical model, just the same intuition, but much more mathematical. And if you like mathematical problem, this slide presents you an open problem. So assume you have a bipartite graph, say, between people and movies. We have n people. We have m movies. Every person likes no more than k movies. So it's binary. Either I like it or not like. Or you can think that people and advertisement and who clicked on what, whatever you like. So, and we can define that person-person similarity is just number of joint movies we like both. And the more tricky thing is person-movie similarity. And let me explain. So if there is a person, and he already liked like 3 movies, then we look at other people who agree with this person that they also like these movies. Like there was person A, and this is person B, who share 2 movies in common and like 1 movie more. And then we decide to recommend this movie to initial person. So we say that probably he will be interested. And we can formalize that by having here a three-step chain between A and this movie X that we would like to recommend. And the larger number of three-step chains between X and A, we say the more similar they are. That's the very, very clean mathematical definition of similarity in bipartite graphs between points in the first and the second part. And then, OK, so to complete the statement, so the query is a new person. So you see animation. So there was a bipartite graph, and the query is a new person. So the query is like another set of K movies that somebody comes and say, I like this, this, and that. And the task is to find person or movie for two-step. So for two-step person, for three-step movie, with maximal number of these chains. And I have clear constraints. So I allow any polynomial preprocessing time for bipartite graph. And for query, I allow only polynomial from K, from degree, and from log n log m. And this is an open problem. So I think it's somewhat relevant to these practical problems I announced in the first slide. And it's very interesting from mathematical side because it's very simply formulated. So let's now move to basic assumptions we have in theory. And sometimes they're really broken in these web applications. So first thing we have triangle inequality usually. Because we say distance, we assume triangle inequality. And another assumption, which I'm not going too deep, that they assume that probably representational dimension is very high, like we have millions of features. But there is something called intrinsic dimension, and it is small. And the current candidate, which is assumed to be the best formalization of intrinsic dimension, called doubling dimension. And the usual assumption that it is much smaller than log n, where n is number of points. But in practice, for many data sets, not for all of them. For pictures, we do not have that. But for movie preferences, I think we have this. And I call it separation effect. And the separation effect, it is the phenomenon that all distances are, say, between 1/2 and 1. So let me give an example. So let's define the similarity between people by number of joint friends. So just my similarity to Moshe is number of joint friends. So we have at least one joint friend, Eli Parat, but maybe somebody else. And so we have this similarity. But then the distance is something opposite thing. So the distance is the smaller it is, the more similar we are. So the distance would be below 1/2. So we will be less than 1/2 similar. Is, say, I have 100 of friends, and 70 of them are shared with Moshe. But clearly, it's not the case. So for most of us, if you look any two people here in this audience, and you intersect the friendship, it would be less than 50%. I think so. And then, so you have almost, for many, many applications, you have all distances in this range. And this broke most of algorithms, because in particular, doubling dimension for this case is very close to maximal possible. So for any data set, doubling dimension is at most log n. So it cannot be more than log n. So in here, it would be log n divided by 2. So it's almost as worse as possible. And the branch and bound algorithms, they cannot use triangle inequality. So they all based exclusively on triangle inequality. And triangle inequality produce no new knowledge. If you take two edges, you know that both of them are at least 1/2. So you know that third one is at least 1, but you know that, OK, at most 1. But you know that it is at most 1 by this separation effect. So it doesn't produce any new knowledge, and you cannot do too much. So the next thing to change in the model is the notion of success. So there is an exact algorithm that produced the most similar, most relevant nearest neighbor. But sometimes we speak about approximate algorithms, which means that if the best candidate is within 1 kilometer and we find something which is, say, 2 kilometers or maybe 1.5 kilometers, then it's still OK. We still find something reasonably close. But with this separation effect, again, it is very meaningless to measure that, because what we have in separation effect, we can just pick a random object. It has similarity. Okay, it has distance, say 1, even worst case 1, but the best has 1/2. So the random object has the approximation factor 2 to the best optimal solution. But it has a factor 2, but it has no relation to what we are searching for. So maybe we should redefine the notion of and what I suggest is approximate similarity instead of distance. And the example would be, so assume you have something like that similarity is 1 minus distance, and you have something like separation effect. Then assume the best thing you have is 20% similar, which is a huge overlap of keywords, say between keyword of interest of the person and keywords in some scientific paper. And clearly, if you find something that it is 1.1% similar, that's a bad approximation for that. So we say that it has only 200 factor of approximation. But if you look for the distances, it has 80% distance, and it has 99.9. And we can say that this is a very good approximation for that. But it is not. So what I suggest is to study approximate algorithms for similarity. So if you would like to use the usual model like Euclidean model, then similarity is just scalar product. So can we find an object that has, say, at most 2 times smaller scalar product with query than the best possible choice? And this is, again, an open problem. So polynomial preprocessing and sublinear search for approximate algorithm for Euclidean space and cosine similarity is an open problem. It is done for Euclidean distance. So for Euclidean distance, for Euclidean space, we can do sublinear search with polynomial data structure, approximate algorithm. But here it's not clear whether we can or we cannot. So that's another open problem. And OK, the last thing I would like to revise is dynamic aspects. So in classical textbooks like Corman, Lyserson, Rivest, and we say that dynamic version of the problem is the problem when we have of search problem like sorting, when we have insertions and deletions and how to handle them quickly. But in the web, we have other dynamic aspects. If we have these networks like hyperlinks or friendship graphs in a Facebook or MySpace or citation graph, it's changing. And even if one edge is changed, it affects a lot of similarities. So if we consider these 3-step chains and one person say, OK, I like one more movie, then all similarities are changed. So you need to rebuild the whole data structure or not. I don't know. Another thing that weights are changing, because we can say that weight for news on dig is number of votes. And it increases every second. And the same with hyperlink popularity in blogs. So if you would like to identify the most popular blog post of today, it gains you backlinks every 10 minutes. So the information comes in very quickly. And another thing that the similarity function is actually not as clear. And domain experts can change the coefficients every day and say, OK, we make another training on another training data set. And now we have new coefficients like relevance formula for web search. And so it's not, the picture is not stable. So you need to have a data structure that can keep deal with all that. So that was the third part. And now we have some time for new results. So for new results, we need one new notion. And that's the most tricky and important slide on the presentation. So I hope you will get it. So this slide is about definition. So the definition is as follows. You have a data set. And I would like to define how nice this data set is. So if it is very nice, I can do I can do fast similarity search. If it is bad, I cannot do. So here I present how to measure the goodness of the set to be searched in. So I take all objects. I take object P and sort all other objects by their similarity to P. So if we have people in this room and we have this number of joint friends similarity, so I take myself, put it in the left, and then sort all of you by number of joint friends to me. So the person number 1 is the person who has the largest number of joint friends, and so on. So in this picture, the person R has rank 4 because he is 4th in this list. And this person S has rank 11, as far as I remember. And OK, so this is the definition of rank. So the rank of R with respect to P is the position of R in the sorted list, sorted by similarity to P. And what I would like to have a triangle inequality for ranks, not for similarity function itself. So for separation effect, the similarity for values has not such a big value, but triangle inequality for rank is very, very powerful. So I would like to bound the third rank. So to compute the third rank, I need to resort everything with respect to R and compute the position of S. And what I would like to have is the following thing, which I call disorder inequality. So the third rank should be no more than sum of 2 previous ranks times some multiplicative factor D. So you have 2 ranks, like, as I said, 4 and 11. And you would like that the third rank would be no more than D times 4 plus 11. And assuming that in the data set of n points where n is very large, you have that this is satisfied for moderately small d, we have a good result. We have a result which is data structure together with Navin Gayal and Heinrich Schutze. We have data structure of size dn log n, and search time is d log n. And the algorithm we use is a kind of this random walk. So it's one of these 4 ideas in work in new model. So we are trying to simulate how people travel in the usual world. So assume I would like to travel from Moscow to Mountain View. So first I go to the airport and check all possible airlines and choose the airline which brings me the most closest place to Mountain View. So I do the greedy airplane choice. And OK, where I go here, right? And then once I arrived here, I try to look not at these large jumps, but a little bit smaller. So I look for, OK, so I arrived to Los Angeles because probably there is no flight to San Francisco. And then I look for trains and take, say, Amtrak and arrive to San Francisco or Palo Alto or where it goes. And then when I arrive here, I take one of the buses. So I look for all buses, and I take the bus that brings me as close to Google headquarters as possible, and then I need to walk. So this is probably the closest public transport station. So if I search all public transport station for the nearest neighbor for the headquarters, that's the way how I find them starting in Moscow. So the data structure we suggested is the set of all airplanes, the set of all bus routes and train routes. So that's the transport. So here it is. So we have some new constant d prime, which is written here. And what we do, so this is for every object P, we should choose several buses, several trains, and several airplanes. So we have these balls, and these are not usual ball, not Euclidean balls. So on Euclidean ball, you have a ball of radius r. That means, all points that within range r coming in. Here it is a combinatorial balls. Means that if it is p n half, means that n half most similar objects to p. So I do not define explicitly the radius. I just say that if I write p7, that means the 7 most closest objects to p. So I write or have in imagination these balls. and I choose d prime pointers. OK, here should be d prime. To this ball, d prime random pointers to this ball and to that ball. So small animation. So I take a couple of objects here. These are my buses. I take a couple of objects in the huge next ball. So they might fall down in the small ball as well. It's possible. So here or here. And then I take random points in the huge ball. So that means that if you would like to estimate complexity, we have n points. We have log n levels. And we have these d prime pointers on every level. That's the size of data structure. And navigation is very simple, the search. We simply start from some point. We'll look for pointers of first level and move to the best endpoint. So we need to check this point, this point, this point, and the initial point, compute the similarity to query, and choose the best. So sometimes the best is the point we are already in. And that means that we do not use airplanes, because we need just go to the train. So we're already in the right country, probably. That's the search. And OK, that was the first result. So the good thing about this result is that it does not require any arithmetic about distance values. So it's purely combinatorial. It's based only on respective order by similarity. And that means that it can be implemented for any data model. So whatever your objects are, whatever your similarity function is, you can, and it's really easy to implement, I hope. So let's move to the second result. And so here we use this triangle inequality assumption. So we cannot do it for any data set. We can do it only for data set that has this triangle inequality for ranks for small constant d. That's my general idea, that the problem cannot be solved in general for any data model without any assumptions. So we need to put some assumptions that are true in practice. And so the second idea is to use probabilistic assumptions. So we knew something about probability of word occurrences in the natural languages. And the illustration I have here, it's called zip flaw. And it says that the word number k by frequency, sorted by frequency, has probability of occurrence proportional to 1 over k. So these are probably not these probabilities, but they are proportional to that. And this is my model of random texts and random queries. So I have these m words, maybe in English, maybe not English, because these zip flaw or power laws, you can find them even outside of natural languages. So they're for many data models, they're true. And to generate a document, I simply independently take every term with these probabilities. Unfortunately, for English text, they're not independent. I know that. But my current result works only for independent. So my proof works. Probably algorithm will still work for real data, but the proof of correctness work only for independence assumption. And the similarity I define very, very simple way by the size of intersection. So given two texts, text means a bag of words, so I do not use any sequence, the order. I define the similarity simply by number of common terms. So I do not introduce any penalty for frequent words. And then there is a very funny theorem proved with Benny Hoffman and Dirk Nowatka, that we can look of two types of overlaps. So assume we have a query. Then, OK, we're, say, searching for maximal overlap. And maximal overlap is, say, three things, 3 words. So say it contains this word, maybe this word, and this word. That's the best possible. OK, maybe this one. So OK, so the best overlap produce you 4. But then you can also look for the maximal prefix overlap. And prefix overlap is overlap by most frequent terms in the query. So maybe it's 3. So there is a document that has this, this, and this. but there is no document that contains this, 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 and this. So the maximal prefix overlap is 3 on this example, and the any overlap maximal is 4. But the wonderful thing you can prove that with very high probability, the size of maximal prefix overlap is within constant factor is something like 1 plus epsilon times the maximal any overlap. So if you search for a document that has the maximal possible prefix overlap, we will find a good approximation, very good approximation for any maximal overlap. But then the last observation is the prefix match is much easier to search. So if you sort all your documents in the data set by the frequency of their terms and just will look for all this. And another thing that the size of overlap is very stable. So it's always within some very small additive factor from this magic level. So we still need probably to understand why it's happened, what significant features of our model that produce that. But I think it's interesting. So I have some questions to audience. So I hope you have questions to me, but I have to you as well. So what are the main challenges in similarity search you deal with? I expect that for recommendation systems or for advertising or for best match search, you have something, and you try some algorithms. So what are the problems? What are the real problems you face? Because I'm interested to learn them, to think about them, and to involve other members of theory community to work on them. And then another interesting question is, what are you using? So probably it's a secret. But OK, the high-level idea probably is not a secret. So you remember this slide with this huge amount of algorithms. So it's interesting what Google is using. And the third thing is data sets. So if there are any data sets that can be made public or provided to a specific research group under some NDA, we will be very interested to test algorithms we thinking about on your data sets. OK, so I have some sponsored links, like Google has. So you can visit my homepage and my special page about similarity search. These are 2 papers. And this is overview in pictures of all the talk. Thanks a lot. I'm ready for questions. Yeah?
Do you have any incremental complexity results? In the sense, if you have a set, you did preprocessing, yes, and then you update the set periodically. So I would like to know, so after each update, which kind of preprocessing can be done, such that you can answer queries. Because typical some problems from incremental complexity point of view are simpler than original problem, like transitive closure, which is polynomial, is it can be done in log space, the Zimmermann result. So there is plenty of research in incremental complexity. Do you have incremental complexity results for this?
Sorry?
Do you have incremental complexity results for this?
I do not know. So that's one of dynamic aspects, and we can think about that. So you mean there are results for insertions and deletions. So if you have new objects, you can insert them to some of these data sets, data structures, and delete. But if the objects are changing, then you cannot do.
No, even if you insert an update. So do you know that after each insertion, how much preprocessing you should do?
So I think they have good results for that, for amortized complexity. So there might be some particular insertion that require a lot, but in average, yeah, they do techniques similar to B trees.
But it's amortized complexity, so it's not incremental complexity.
Yeah, I think so.
OK, thank you.
Yeah. You can answer my questions if you do not have any your questions. I can show you them.
Well, I guess everybody understands everything. So this is really good speaking. So let's thank him again.
Thank you.